Right, hi everyone, let's start. Today's lecture is going to be quite packed, and we're going to talk a lot more about uncertainty. So first, we will see how mixed states evolve if you have uniform dynamics, if there's something like the Schrodinger equation, but for mixed states. This will be very simple just to warm up. And then we'll go into the main topic, which is uncertainty about evolution. So when we don't know what the global evolution is, and this will be modeled by something called quantum channels, we need to find, well, I'll tell you about two decompositions of them and how they relate to each other. And then we'll see an application, which is how we can model the effect of physical measurements, which we've been talking about a lot, as a channel in a system. Today, we'll just see a very simple example of this. And then if we have time, which means the break will be very short, I realize I still need to cover uncertainty relations and Heinsenberg's uncertainty relations. So we'll talk a little bit about this. Okay, and you might be thinking, now that the lecture starts to be fun again, it's the end of the semester. And I know it's true. But the issue is that, all of this that we're doing now is adding on top of the theory, right? We have this theory for pure states and unitary evolutions and very simple measurements. And then on top of this, we're adding now all these notions of uncertainty, right? So now we have all this more formalism. Now, of course, that when we discover a new theory or you propose a new physical theory, you don't start by, extending all the possible ramifications. First, you need to test that it does what it should do. So for example, you go and make experiments in the lab with atoms and so on, and like the double slit, and see if this theory, this formalism that you come up with can explain the physics in this setting. Right? That's why we spend so much time talking about physical settings, potentials, and so on, and the hydrogen atom and all of this. It's a necessary thing. Otherwise, we're just like, I don't know, like creating a new board game and then seeing all the expansions, which is a lot of fun, but we needed first to connect it to the physics. So that's why we spent the first part of the semester doing that. And now we have all this fun stuff. And we still have some time to talk about it. So let me just recap very quickly what we did last time. So we saw that if you have uncertainty about a state, you can represent it as a mixed state, a density operator. We saw that it evolves under unitary evolution like this, right? And we saw that we then, so let's call this tick. If we measure it with some projectors pk by k, then we know that the probability of getting k for this rho prime is trace of pi k. Right. Okay. Then we also saw that, well, in particular, maybe this can be seen as this state can be seen as just like I'll reduce information about something that is actually a global state over a larger system. And this idea of forgetting some information, so ignoring everything that's happening on system B and the correlations between them, this is expressed by the mathematical operator partial trace, so trace over B. Might we saw to describe this. And again, I emphasize this is not a physical operation, it's really just we ignore this. And then we saw that for the special case where they evolve under some kind of, an evolution that can be decomposed into products. So on one side, something happens, on the other side, something else happens, there's no interaction. Then this goes to, as before, we can do unitary evolution like so. And this, we can from here take again the partial trace. And in this special case, we get precisely this object here. And we can also compute the probabilities for a measurement outcome, right, of this new state, rho B prime. And here we just consider the pk tensor identity. As like the global view of the local measurement. Okay. So we saw that this all works out. So what have we not seen yet? Well, the first thing we'll see is what if this UA has a very nice form? What if this thing here is just uniform dynamics, like we've been seeing for most of the lecture? Then is there something like the Schrodinger equation for the density matrix? So this will be the first part. And then the second part is like, okay, what if this global unitary is not of this form, right? Then for sure we cannot just this does not commute, right? We can't do this. Or what if instead of having here a unitary that we know, we just know that with some probabilities some unitary was applied. This is very common, for example, if you're modeling noise with some interaction with some environment, right? I leave my cup of tea out here. It interacts with the air in the room, and I don't know exactly what unitary is applied, right? Because there's a lot of uncertainty about the state of the environment and so on. But we can make some kind of effective map saying, well, this cup of tea will cool down, for example. Right? So there's something we can say here. So we'll talk about all of these things. So first we will warm up and just talk about the case, the simplest case, which is when this is the respects uniform dynamics. So we will skip a few pages because I want to do the uncertainty relations last in the break, maybe. So we go to page 7 of the lecture notes, and that's the Schrodinger equation for mixed states. So if you remember, what we did a long time ago is that if you have uniform dynamics, and what it does mean that the Hamiltonian did not depend on time, right? Then we looked at the Schrodinger equation for pure states. So not necessarily the energy eigenstates, but any arbitrary pure state. And then it was this d dt t equals minus I of h bar h check, right? And then from here, we saw that from here, we got the unitary. We saw that we could write u of t as a unitary of t in the initial state, psi of t. And this unitary was given by the exponential of the Hamiltonian, right? So now what if we have a mixed state? I mean, if we have rho of 0 and the dynamics are the same, so the Hamiltonian is the same, then we know from what we saw in the previous slide that this must evolve to in the way that we saw before, right? It's just a specific case of a type of unitary. Now, in general, maybe this is a bit complicated. Maybe this is a big multiplication to do, and we want something simpler, so something more like the Schrodinger equation directly. Okay? So then we will do exactly that. So our goal is to get an expression like d dt of the density matrix is some function of what are the only parameters here. I mean, it's only the Hamiltonian and the density matrix at this time. Okay, so we're going to find this. What is d dt? What's the definition of the derivative? Well, this is the limit when you have a delta going to 0 of rho of t plus delta minus rho of t, all of this divided by delta, right? Okay, so now what is rho of t plus delta? Well, this is the unitary applied on for a time evolution of delta applied on my state at time t, right? So if this is time, I have here rho of t, and then I choose a very small delta, and here is rho of t plus delta, right? And this is the u of delta. Okay, u of delta. And now, well, what we do is what we do always. It's like we have this unitary as an exponential, so we're going to expand it in the Taylor series on time. So we have u of delta is e2 minus I delta over h bar h. And this is what, well, I just expand as an exponential, so it's the identity minus the linear term on delta I delta h bar h plus all the other terms, and I just say, well, this is all order of delta squared. Okay. The idea being that later when we put it here, and we take the limit of delta going to 0, this is going to disappear. But for now, it's not an approximation. This is true, right? I'm just not specifying what's inside here, but this is absolutely an equality. Okay. So now we just compute this thing here. Oop. So now what we have here, so we have identity minus I 2 over h bar h plus order of delta square rho of t, and now the same thing here. Identity, but because it's u dagger, and there's a, so the h is Hermitian, right? So h equals h dagger, but the minus I becomes plus I because it's the conjugate. Plus I delta over h bar h plus order of delta square. Now, this is a lot of terms, but what we'll do is we're going to group all of the ones that are order of delta squared or higher powers of delta. We're just going to group them into here. Okay, so then let's see what remains. So we have the term that takes the identity from here, this, and the identity from there. There's no deltas there, so this remains. So we have rho of t. Then we have the term that takes this identity from here, rho of t in the next one. Perfect. This has only one delta. So what is this? So it's identity, rho of t, h, and then I delta over h bar. And then we have the term, well, identity, this and that. This is already delta square, so this is already inside here. Then we have this term, so we have a delta here, the rho and the identity, so this also survives. This is minus I delta h bar, and then we have h rho of t identity. And then all the other terms. So for example, you have this one, this already has delta square, right? It has delta twice, so it's already in here. And all the other terms, of course, this times this, all the other terms are going to be gobbled up by this term. Okay. So then we only have these two things. So what is this? On the one hand, we have rho of t, and on the other hand, we have, maybe I write it like minus I delta over h bar, and then we have h rho minus rho h, because there's a minus sign there. But that's just the commutator between the Hamiltonian and the density matrix, which is nice. Okay, so now we just need to plug it, to plug this thing into our formula. So let's do this in the next page. Okay. So what is this then? So this is the limit of delta going to 0 of, so we had rho of t minus I delta over h bar, and then this commutator. Oh, I don't see the chat. Commutator plus order of delta squared. Oh, did I get rid of the order of delta squared? Sorry. Plus order of delta squared here. Good. Minus this rho of t that comes from above. That's this one. All of this divided by delta. Right. So these two cancel each other. So we have here, this should be a delta. So then we have the limit when delta goes to 0 of what? Minus, here this delta cancels with this, so we have I over h bar h rho of t, which is great because it does not depend on delta. Plus, then we have this term, so order of delta squared divided by delta. This is at most order of delta. And then when we take the limit of delta going to 0, this term is constant, doesn't change, and this term goes to 0. So then this is just minus I over h bar h rho of t. And this is the Schrodinger equation for mixed states. So let me just write here. So this is important, in particular because next time we'll see what happens if now the global evolution is not uniform dynamics, but it's something that is more or less uniform, just not unitary. So for example, I say, look, I store my spins in a hard drive and there is some noise, but I model this noise as kind of constant over time, or like the noise rate is constant over time, for example. And then we'll get a generalization of this equation where then we have here some noise terms. So we keep this for now. This was just a warm-up. And in particular, so what happens if it's a pure state? Then we recover the usual Schrodinger equation, because let me just, let's put them side by side. So this is for mixed states. And this one was for pure states. Right. So what happens if I have rho being a pure state, meaning I represent it like this? Well, then what do I have? I use the equation on the left, so I have d dt of rho of psi of t minus I over h bar h, and then I have here psi of t, right? And now this is very simply, on the left, what do I get? Well, again, it's a derivative of a product. So this is a vector that goes like so. This is a vector that goes like so. So it's just a derivative of the product. So what is it? So it's dt of the first one times the second plus the first one times the derivative of the second. And on the left, what do I have? I over h bar. So the first term is going to be h of t psi of t. And then I get plus I over h bar Let me put the I over H bar at the end. Of T, H, and now I over H bar. Right? Here I just, this is the commutator, one minus the other, so they get different signs here. But now, if I look here, I have this thing is this, right? According to this equation there. And then what's left, it's that, sorry. So this whole thing. The derivative of the pure state on time is given by this from the pure state Schrodinger equation. And then of course it's multiplied by the bra, which is also here. And on the right, we have exactly the same. So this thing here is this, with just taking this equation, taking the transpose conjugate. And then of course there's this term lying around, but it just comes from here, right? So they're perfectly compatible with two of them. Okay. Which one to use? Depends what you know about your system, right? Most of the time you don't know the exact pure state. So you'd be better off using this, but on the other hand, this is more complicated to compute. So sometimes one just approximates it by the pure state. Okay, so that was that. But now let's talk a bit more about uncertainty about global evolution. So that was the warm-up. If there's questions about that part, please let me know. Now we're in the break. So first, let's just motivate this. So let's give some examples. One could be that you give this state rho to someone, or you store it somewhere, you know, it's a machine labeled E, and all you know is that it applies with probability pi, it applies the unitary ui, right? And then something comes out of it, it's still a quantum state, right? Rho. And what is it? Well, in this case, it's going to be, it should be something like, well, probability pi, it should be ui rho ui dagger, and you want to represent this as a map on the original state, right? So it's like, I don't know, maybe it is some noise, and I don't know with some probability what's the exact evolution, or maybe I give this box to my friend and I don't know which unitary he applied. Okay, so there's many cases like this. The other one that we saw is that, well, maybe there's rho on S and some environment. So here's S, here's the environment. Maybe I even know what the global state, what the global unitary is, but I don't know what the effect here is on my reduced state, on this state, right? Just on S, if at the end of the day, I just ignore the environment. Or, you know, maybe I'm allowed to ignore whatever I want, right? This is an operation that happens in my head and in my notebooks. So maybe I ignore if S is 1 qubit and E is 10 qubits. Maybe at the end, I want to know what happens not in S, but in some S prime. Maybe I want to know what happens to the first 2 qubits. Something like this. So all of these things, I would like to have some kind of mathematical object to model them. Right? Another example that's maybe very practical is if you send a state, you send some photons through some optical fiber, you know, and you'd like them to arrive at in the same state as they went in. But of course, there is some noise in between. So you want to be able to model this noise as a map from density matrices to density matrices. So what we want to know, we're looking for some mathematical objects. maps. So what should they do? Well, they should go from density operators in some Hilbert space to density operators. In principle, could be even a different Hilbert space. Because like I said, I'm always allowed to ignore more. So they take some row A to some A. Let's call this row A took. Good. And what should they satisfy? One, they should be linear. Because, well, what happens if I don't know? So if I don't know for sure which state I have, right? This idea of I'm taking a state and I know with probability pi, it's going to be one of these. Well, then for this to be physical, then for sure when I apply this map, this channel, this physical evolution, and at the end of the day, this should be the same as applying it to each of my possible quantum states and then taking the mixture, right? This is just, it respects this probability knowledge structure. Two, I mean, it should map density matrices to density matrices. So in particular, it needs to be trace preserving, meaning that must be the trace of row A, right? I mean, if I start with density matrix, it's normalized, meaning there's a different eigenvalues give me probabilities if I made a measurement to get the different outcomes. So then, I mean, if the outcome of my channel is still a physical state, it should also be normalized. And the other thing that it needs is that it's completely positive. So let me tell you what this means. So I told you before that the density matrix has all positive eigenvalues. It's zero positive because again, they correspond to probabilities. So then when I apply this map on my row A, well, then for sure, it must still be a positive operator. But more general than this, if I apply this map, if I have a joint state of row A and some environment B, and I apply this map, goes from A to A prime in the first system, and I do nothing on the second, so this is the identity map, then this should still be a state. Then this should still have positive eigenvalues. It is a strictly stronger condition than the other one. These things are studied more carefully in QIT. But this is really this idea that, well, I have some row AB, here's system A, here's system B. And then if I apply the map here and I do nothing there, at the end of the day, I should end up with a state row A prime B that should still be a valid state. So there's maps like, for example, the map that takes the transpose on state on system A of the matrix. It is positive, so it's true for this. If I don't put the identity here, but it's not completely positive. So we need this. Okay, so, and then, I mean, it should satisfy these conditions that we saw before, right? So in this case, it should be consistent with our modeling of what's happening here. Okay. So I'll tell you what the theorem is, and we'll not prove it. Maybe we'll prove parts of it here. If you want a much more detailed construction of this, you should take the quantum information theory course, where we go over this in detail. So here's the claim. But we'll look at examples and we'll see interesting examples that you don't see in QIT. Oh, so maps that satisfy all these things, they're called trace preserving completely positive maps, also known as TPCPMs. It's just literally these conditions. So here's the following. Every TPCPM, so if it goes from A to A prime, admits the following non-unique representations. This non-unique thing will be important later, and it's also an if and only if. So let me just tell you what it is. First, the simplest one to understand physically is a Stinespring dilation. This is the idea that every map, every quantum evolution is deep down, it's a reversible evolution on a larger system. We're just ignoring part of the information. So let me put you like this. I'll explain what this means in a bit. That whenever you have a map, even if it's irreversible, right? So it could be a map, an example of a map would be just a partial trace, right? Like I just take a full quantum state and then just ignore a subsystem. This is not reversible, right? It's a many-to-one transformation. Even classically, imagine you have a bit string and you just ignore half of them, right? You cannot go back to the original bit string. And many evolutions in life, they seem irreversible, right? You break a glass, you leave your coffee cup to cool down, and you cannot go back on this. Right? But the magic thing is that every physical evolution, so every map, actually has a reversible version. It's just in a larger system. Okay? Meaning, like, if I have access to all the gas particles in this room, and I could apply any unitary here, I could actually reverse the cooling down of my coffee cup and get hot coffee again. But of course, this is never feasible in practice, right? So the idea is that for every map from a system A to A prime, so here it is the map, right? Take A, there's always some kind of environment that I can initialize with state 0 and some joint unitary on UA and E, such that at the end of the day, I just apply this big unitary and then I trace out part of it. So let me write this more explicitly. So if I have my global Hilbert space. HE, which, like we said many times, there's many ways to break a cake, to slice a cake, so we can also break it into these different subsystems. Okay. And now the idea is that, so for example, maybe, it's 10 qubits total and you have 5 and 5, but at the end of the day, you only care about 3 qubits and you ignore the other 7. Something like this. So every map from A to A prime of rho A can be written as trace over this last environment of this joint evolution. So U E rho A tensor the zero state in this environment. Okay. Now, this is a very, very important result with many implications in physics in general, because it says, look, nothing is irreversible. In particular, the global entropy of the world is not increasing. All that's increasing is our perception of entropy. Things like the second law of thermodynamics, for example, there's this idea that things always get messier, right? Maybe you've heard this, like the universe will end up in a heat death, meaning everything will be like a warm soup. This all come from, you actually have a reversible operation overall, but you're just ignoring information because maybe we'll have access to local observables. Right? So it looks like something irreversible here, but there's always a global view. Okay, good. So one way to simplify this is to say, well, if we look here, if I just take, let's make a box around this part here. And this thing is also a reversible operation, but it's now from a system A to A prime E prime, which means it's not exactly unitary because you change the dimensions, but it's still reversible. So what it is mathematically, it's an isometry, and I'll explain what it is in a second. Let me just rewrite it like this. So of V from A to prime acting on A. And here's the same V, but the diversion. So what I mean by this is the following. This whole operation of bringing in a state, an environment in a zero state, applying a unitary, this is reversible, right? This I can go back to doing this. Let me think of a classical example. I don't know. So suppose that you want to go suppose that the whole map takes row A and ends up in zero state, in this 0, 0. No matter what the row is, it just erases it, just resets it to 0. If there are restrictions or requirements for the size of the Hilbert space HE, yes. Yes, I mean, apart from these dimensions having too much, the statement is that there exists HE, and there exists a U, a E, and there exists the H prime, such that this follows. And depending on the map, in many cases, E needs to be at least as large as A. But you go into this in more detail in QIT if you want to have a look there. Yeah, so for example, in this case, I was going to say, so imagine that all this map does is always reset it, completely irreversible, right? So it takes any state and just sets it back to 0. It's something I can do in the lab, right? One way to do it is to take some state 0 from some environment, an auxiliary system, and here this unitary would be just unitary that swaps the two, right? So before I discard whatever is here, which would be my original row, I can always reverse this part of the operation, right? I can go from the state that is here, so this would be what be 0 here and row A there. I can always revert back to this original situation. From here, I can always get rid of this for free. So this This is a more compact way of representing the global thing, where we don't need to put this down explicitly. So what is an isometry more precisely? So if it goes from A to A prime, B prime, what it means is that if I apply it like this, I get the identity in the first system. And if I apply it the other way around, oh, this is wrong. It's the other way around. Sorry, it's wrong on the lecture notes. So it's the other way around. So this is A prime B prime, and this should be identity on A. On A. So it should satisfy these two things. So meaning I have my state on my state row A. So I have my state row A. I apply V, then I apply V dagger again. Should be the same as doing nothing. It's easy to see for pure state. But if I have some state here that lives in A prime, E prime, and I apply first this, now I'm in A, now I apply it again. So what these are, so these are, unitaries are always square matrices, and isometries are always rectangular matrices, right? Where these dimensions here are the dimensions of input and output spaces. And what they correspond to is like perfect compression or dilation of information, right? Nothing is lost. So it's reversible, but you can change the dimension. Okay. So this is the more physical way to look at it, of a map. Even irreversible maps can be seen as reversible maps in a larger system. This is great. This was number one. So number two, which is more used for practical purposes, is the Kraus decomposition. And that's the following, is an explicit way to do this without going to a larger system. It's just saying, well, this must be the sum over K of EK or A EK, where these operators, again, these are rectangular operators. They go from A to A prime, and they must satisfy the following rules. So they must satisfy that they sum up to the identity in this following way. EK, EK. Okay. They are called the Kraus operators. And so each of them, so it's a rectangular matrix, like I said, it goes from HA to A prime. So, and I will prove soon we'll prove that if it has this kind of decomposition, then it satisfies this price-preserving, complete positivity, and linearity. We will not prove the other way around. This you can do in QIT, but the truth is, it goes both ways. So if you can write a map in this form, then it's a TPCPM, and if it's a TPCPM, you can write it always in this form. And this decomposition is not unique, much like this decomposition is not unique. And one way to see it is that, I could always apply now here the second unitary just on this environment system, and this will be traced out, right? So it's not noticed by this, so it's still the same map locally, but the global implementation is different. So what's the physical meaning of saying that these decompositions are not unique? So let me just tell you first what the relation is between the two. And that's simply that we can write this isometry as a sum in case of E case K1 E prime, where this case form a basis. So for HE prime. So to come back to your question, you were asking if there was any restrictions on the size of this environment. And one of the ways to think about it, in the case when this dimension is the same here, right? We're not doing any additional trace. One way to think about it is that you need at least as many states, independent states here in your environment as you have Kraus operators in the cross decomposition of the channel. One extreme example, say this map is just a unitary map. Then this is just U dagger. It definitely satisfies this equation because U dagger U is the identity, right? And then here you just have, you don't have a sum, you just have here U, and here you just need a 0. So this system can be trivial, just needs one basis element, right? However, as it gets more complicated, more and more irreversible, you need more states here. Because one way to look at it is like, well, this is almost like applying some operation with some probability pk that is hidden here inside these operators. So I need as many basis states in my environment as I need to keep track of which one of them was applied. Yeah, we'll see an example later that makes this a bit more obvious. Okay, we go for a break now, and it will be very short. Let's give it a 5-minute break, and we restart at 7 past. I'm here if you have questions in the meantime. Okay, so let's restart. Because if we restart now, I think I can even do the uncertainty relations today. Good. So we had these two decompositions, and now we're going to show. I mean, I just gave you out of nowhere, and I need to at least gain some goodwill from you by proving that some things are true. So of course we'd have to prove what? First, that all maps can be written in this form. Second, that everything written in this form is a map. Although this is actually direct, right? Because yeah, this is direct because this is of course a density matrix, and because it's just unitary evolution of a density matrix, and then if I take the partial trace, it's still a density matrix. So that's clear. But I have not shown that every map can be written in this form. And then I'd have to show that every map can be written as a cross decomposition, and that every cross decomposition is actually a valid map. So we're going to do this last step first, and then we're going to show that this relation works, which gives us, at least part of the big picture. And for the other proofs, CQRT, I don't know if they're in the lecture notes of QPM. Maybe they are. So first we need to show that this cross decomposition gives us a valid map. So we need to show that it's linear. And then we just do it directly. So we have the map applied on what we said, if I have a probabilistic mixture of states. And I apply the map. So what did I say? This was sum over k of ek. Now comes my density matrix, which is the sum of density matrices. Okay, dagger. But this because, all these matrices act linearly, I can exchange the sums. So then I just have, the sum over I, pi, of sum over k, okay, rho I, okay, dagger. But that's just sum over I, pi of the map applied on rho I. Right? Okay, so that's the first thing. The second one is that this decomposition should give me a trace preserving map. And it does. So we need to say that the trace of rho applied, the map applied to rho should still be the same as the trace of rho. Okay, but this is just a trace of ek, sorry. Oop. Sum over k, ek, rho, no, rho is now, ek dagger. And now we just play with the trace, right? So the trace is linear, so we can take the sum outside. Trace of ek rho, ek dagger. Now comes this very convenient property of the trace that it's cyclic. So I can take one of these operators and move it to the other side. So I have sum over k, trace of ek dagger, ek rho. And now the trace is linear again, so now I can move the sum inside. So then I have trace of sum over k of this thing. Rho. I mean, rho does not depend on k, so I can put extra brackets here. But now this, by definition, this is normalized, this is just the identity. Right? Because this was really the definition of the cross decomposition. We said it must satisfy this relation. And that's why, this is why. It's so that it's trace preserving. So this is just trace of rho. Okay. Seriously, the trace is really nice, that it's cyclic and linear, so we can always, if you have a sum inside and it looks funny, you can always do this. Take the sum out, move things around, bring the sum back in. It's a joy to work with. Now we need to show that it's completely positive, so we take let's take some rho A in some environment, right? And we can always write it in the spectral decomposition as a sum of pure states, so a mixture of pure states. These are still pure states on the two systems. And what I want to know is what happens if I apply E from A to a dagger, that's doing nothing. Or the second system to this state. So the cross decomposition of this map, well, the cross decomposition of the identity, it is just a unitary operator, and the only cross operator is the identity. So then when you do the tensor product of the two, it just becomes sum over k of ek, that's the identity, on E, over E, ek dagger. That's the identity. So this is what we have. Well, and now we just write again, we just expand rho AE. So we have, let me just copy this again. Sorry for this. I think I save time like this. IPI. Now, again, the sums can go out. And now we have what? Sum over k of now this thing that comes here, which is ek. Those are the identity. So you know, here, ek dagger, those are the identity. And this looks a bit messy. But one way to look at this is say, well, this is just a matrix applied on a state. So it's going to be another vector. It's a state. So this is some psi prime. And this is another state. Okay. And now these are all larger than 0. And this is just the state. And this turns out to be also larger than 0. Okay, I'm sweeping some details under the rug here, but I'll ask to do this more carefully in the tutorial. So what this means from here is that if you have the cross decomposition, if you can write it in that way, then you get a valid quantum channel. Quantum channel is TP-CP1. And then let's prove the claim. Let's prove now the relation between the two. So first we need to say that V like this is an isometry. So we need to look at V dagger V and at V dagger. So here we're going to look just at V dagger V, because you'll do the other one in the tutorial. It's a bit more involved. So we do this. What is this? Sum over k, ek, dagger. Okay, right? So it's the dagger version, and now here, sum over a different letter, L, E, L, L. So then is k, sum over k and L, and you have in the first subsystem, ek, E, L, and in the second subsystem, we just have this this inner product, which is delta KL. So then overall, sorry, let's move this down. So then overall, what we have is sum over k of EK dagger, EK, and then once again, this is the identity because that's the normalization condition for the cross operators. So in one direction, it looks like an isometry. If you do it the other way around, it's a bit more annoying to see, but it's also clear that you also get the identity. Okay. But now it should still give the right map, right? So now we need to apply it here. And what we do is the following. So let's say, what's the trace over ETH of when we apply this, E dagger? What's the trace over E of now the whole thing again? So sum over K, EK, K, rho A, and now sum over K, sorry, different letter, sum over L, L dagger, L, okay. Now, look, this is a bit of a mathematical abuse because, of course, this lives only in one system, and what this is really is a map from this system to A prime, E prime. But in terms of multiplying matrices, it's easier to look at it this way. So anyway, so this gives us trace over E of what? Sum over K and L. On the first system, we have AK, rho A, L dagger, and on the second system, we have K. But then, what is the partial trace? If you remember, this is sum over some other letter. What did I use? J. Is the identity in the first, which is A prime now. And J on E prime. Then this whole thing. And then identity on A. Tessor J, right? This is the definition of the partial trace. And then what happens as usual is that this J encounters this K, so it gives you a delta. This L encounters this J, so it gives you another delta. So overall, the only terms that survive is when J equals K equals L, so then you end up with sum over K, EK, rho A, EK dagger. Is that clear? Why? I don't need to do it step by step. It's step by step in the tutorial, right? In the lecture notes. It's just this acts here, this acts there. There are deltas. So we can get rid of two of these sums and so on. Good. Now, please take into account that I said that for every map, you can have different cross operations, and each different cross decomposition, as we see here, corresponds to a different global isometry. Okay, so it really means that if I want to implement this map physically, it gives me different physical implementations. However, the local effect might still be the same. Now, I wanted to talk about applications to measurements, because we talked many times about how measurements are physical evolutions. And so how did we see this? Always it was, we have some psi on the system S, and we bring in a pointer in a well-prepared state, right? It's like a Gaussian. And then to measure some observable A on the first system, we did some interaction here, right? And then they are both here again, right? So for example, you interaction could be e to minus I, some constant g, there's the coupling constant, and then the observer will want to measure on the first system and something on the second system on the pointer that makes sense, right? So for example, it could be the x or the p, we look at this too. And then we saw that, well, what happens at the end is that they get entangled, these two, and they get correlated in the basis of this observable, right? And then therefore, by looking at the pointer here, we can determine what the probabilities are, for example, what the measurement statistics for measuring A on the first system, right? And this is how we implement all measurements. And now the question is like, what is the local effect here? So this is exactly the same structure we saw before, where we can model the effect here on just the system as a map epsilon, right? And this will tell us how disturbing this measurement is. It will also tell us kind of what does an outside observer, so suppose that Alice makes this measurement and she knows the outcome because she has access to the pointer. But Bob only knows that she did the measurement. So he knows that she did this, but doesn't know what Alice then measured here. Right? So what is his information about the state of the system now? And this will all turn out to be modeled by the same object. So this is kind of a complicated unitary interaction. So we're going to look at the toy model. So the simplest case, which I told you, which is they're both qubits. Okay, and we can do the more general case where this is rho. The pointer starts in some state 0. And the interaction between them is just a CNOT. Right? And we saw that this corresponds to a perfect measurement in the Z basis. And now we want to know, well, what's happening here? If I now ignore this, so let's say I ignore, so the symbol normally means I take the partial trace, so I ignore the pointer. I just want to know what's happening there. Okay, so then let's do this, because the result is quite nice, and it's also an example for all those decompositions and so on. Here we start from the global view because we already have it, right? So what is my unitary SP? Well, it's just a CNOT. What's the CNOT? If you remember, it's like if the first qubit is 0, then do nothing on the second. But if the first qubit is 1, then flip the second with a poly X operator. So here's a more compact way to write this is just sum over J. Okay, going from 0 to 1. K on the system, tensor X to the power of K on the second one, right? Just because in this case, you have X to the power of 1 is just X. X to the power of 0 is just the identity. So it's just the same way of writing this, except later on, it's just more compact. And let's take rho S to be any density matrix for now. So how do you write it in general? We don't know what basis it is diagonal in, so you write all the coefficients, right? This is corresponding to just saying it could be 1, 1, 2, 1. I never know. I don't want 2, 2, 1 or the other way around there. Okay, so then what is rho SP? This is rho S, and then I bring the pointer in state 0. So then this is just sum ij, cij ij, and then tensor 0, 0. Okay, so what we'll do is first we're going to go from rho s tensor 0, 0. We're going to apply here the USP, right? So we're going to get the state USP OS 0, 0. And then we're going to trace out the pointer, right? And this should give us a map, epsilon, right? Because this is exactly the definition of the Stinespring dilation. So we're going to do it this way, which means we need to apply this operator here to this matrix there. So we do it. Okay, so we have, what's the evolved state? USP dagger. So let me just copy these things. Okay, one thing to notice is that the Pauli matrix X is Hermitian. So if I take the dagger, it's the same as taking the matrix again. Oh, it's not going to fit, is it? Okay. Okay, this definitely save time. Okay, so we have all this. Let me change this sum here. Just use a different letter. Let's use here L. L, 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 L. Look, there's easy ways to do this. You can just also write this unitary in matrix form because it's only a 4x4 matrix and just multiply all these matrices together. Right, that's easier, but why not do it this way? So we have a bunch of sums, K, L, I, J. Then what do we have? On the first system, we have K, K, I, J, L, L. On the second system, we have X to the K, 0, 0, X to the L, and then we still have this coefficient C, I, J. Okay, so we have one delta here and one delta there, J, L. So we can get rid of two of these sums. What did I keep? I kept I and J. So we have C, I, J, and then we have here I, J in the first tensor, X to the I, 0, 0, X to the J. And now it's when this notation stops being useful. So let's go back to more easy ways. So when I is 0, what is this? This is just X applied on 0. So it's X, which is a 0. And when I is 1, this is just X to the 1 on 0, which is just 1, right? So actually the state you get here is the state I, and so this state is just state I, and this is just state J. So overall we get what? Sub over Ij, Cij, and then we have I, J in the first tensor, J in the second. This is a very related matrix. If you look at it in matrix form, it will, so it's 4x4, but it only has elements here in the corners. Okay. But still, I don't know yet what this means. I can tell you already that in the special case where, you know, the thing I was going to measure, this, this was, for example, the plus state. Then what I get here after this is just the Bell state, right? It's going to be 0, 0 plus 1, 1 over square root of 2. And this is a generalization of that for any state. So now all we need to do now is take the partial trace, right? We've done this part. We need to go down now. That's the easy one. So trace over pointer of my evolved state. Let's just write. Let's write what the trace is. So the trace is the sum over K, identity on S. Tessor K. Now here comes the state, and at the end is going to be identity on S tessor K. Let's plug in the state. Okay. Paste. So, okay, this thing. Good, and it's going to be again a bunch of deltas, right? So this is sum over K, sum over Ij, Cij of nothing happened in the first subsystem. We just have Ij. In the second one, you have this in the products. Right. So of course, at the end of the day, this thing here is a number, so this tensor product becomes redundant because the second system is just trivial. Right. Okay. Which is what we wanted, right? Because we want a map just on the first system. So we have the sum over K, KK, and CKK. Okay. So what does this tell me? Well, if I started with the density matrix, if rho was of this form, it's C11, C22, and here's C, let's say this is 2, 1, let's say this is, no, this is 1, 2, I'm sure this is 2. Then it means under this map, it evolved to having just the diagonal elements, right? It lost all the off-diagonal elements. Which means, in particular, it becomes more mixed. But this is not so important. What's important to think about is what these coefficients are. Because in fact, CKK is a trace of rho. Why? Because it's, okay, this is the same we saw when we first defined density matrices and talked about the trace. This is the same as this, which means taking the density matrix and sandwiching with this projectors and getting only this coefficient. Or if it's 2, then getting only this coefficient. But but what is this? So this is the probability of getting outcome K if I measure with these projectors, okay, on state rho. Okay. So then what I got here is like, so this is the sum over K of the probability of getting outcome K times, I mean, the post-measurement state, right? Remember that if you measure in the Z basis and you obtain 0, the post-measurement state is going to be 0. If you obtain 1, if you measure again, you better obtain 1 again. So the post-measurement state is 1 when we first talked about these things. Right? So what this is from the perspective of, imagine Alice did the measurement. She's inside here. So she's the person who has access to the system, right? So she performs the entangling operation and maybe later she measures this. So she knows what outcome is. Bob only knows what operation she applied. So his description of the final state is like, well, I know that with some probability, Alice got outcome 0, which means that now the state is 0. With some probability, Alice got outcome 1, which means that now the state is 1. Right? And that's exactly what this encodes. So when we have a measurement and you ignore what's happening in the pointer, so in your measurement device, what you're left with is this probability description of what the possible final states are, right? Now, the CNOT is a toy example, corresponds to a very sharp measurement. What you'll see in the tutorial, maybe we'll also talk a little bit about this on Thursday, is what happens if now you have a weak measurement. Remember, so the final states of the pointers are not orthogonal for the different outcomes, they can overlap. And it's called a weak measurement because the disturbance in the state itself is very small. So you will see that then this final state is very close to the initial state, right? It's not as tough as this map. So this map comes here and like really kills off all these off-diagonal coefficients. And if it's a weak measurement, then it just changes them a little bit. It gets a bit closer to this, but you still have a state that is quite similar to the initial state. Good. So that's something we should look into in more detail. So I don't know yet if I'll shuffle it all to the tutorial or I'll do it some in the lecture on Thursday. In either case, it will not be in the exam. So what's left to do here is now, apart from looking at more examples, is now to do this generalized case that I talked about where you have the Schrodinger equation, but now with some noise. This we'll do for sure on Thursday. But before this, we need to talk about another type of uncertainty, which is the uncertainty relations. So I don't like to talk about it in one lecture because this is a much more subtle subject than is shown in most QM courses. And I think maybe I'll talk about it in the advanced QIT course next semester. So, but what is the idea? So now we go back to page 2. And I'll give you just an overview here of what happens. So suppose that we have two observables A and B. And now suppose first that they commute. For example, the total angular momentum and the angular momentum in the z direction. So this means they're jointly measurable. What does that actually mean? It means that it doesn't mean just that it's the same if you measure one A first and B then, or B first and then A. It means that there exists some observable C that you can just measure this observable C, and it's like a more fine-grained version of the other two. You do this, you do some post-processing, and you can obtain the statistics for A and B. Let me give you a very classical example. Okay? So suppose you have a die that you want to throw, and the observable A just measures, is the number even or is it not even? And the observable B measures, is it a multiple of 3 or not a multiple of 3, or just what is the modulus, what is the rest modulo 3, right? So there is obviously a more fine-grained observable, which is just, I throw the die, I look at the number, and from this number, I can obtain these other two observables, right? From the number 5, I can tell you, oh, it's odd and it's not a multiple of 3, right? So you'll show what this means precisely in the, or you'll prove this precisely in the tutorial. But now first let's talk about what happens if they are not joined, if they don't commute. And then you think, oh, if they don't commute, then we cannot measure them jointly because we cannot do either measuring just one or the other way around. And there isn't one such observable that you can get perfect statistics about the A and B from post-processing of this one. Yeah, but the thing that puzzled Heinsenberg is that this seemed to contradict what he saw in the lab, because in the lab there were things like this particle chambers. So you have a bunch of gas and you want to detect some subatomic particles that are flying around, and what you get is you get a picture on a silver plate of kind of the trajectory of these particles, and these are very pretty pictures. Maybe I'll add a picture for the next class. Right? And from here you can derive properties of these things, right? You change the magnetic field, you see how much they curve. This tells you something about their spin, so on. Right. But what puzzled Heinsenberg is like, well, if we can observe the trajectory, the only way to observe the trajectory is to measure both x and p, right? Because x gives you the position, p gives you the speed. And if you know the trajectory, you must know x and p, right? However, x and p do not commute, right? This is, the commutator is given by this. So it looked like a puzzle. So what he found out is that, in fact, when you have this, then the product of the uncertainty of the two observables, and I'll write what this is, must be larger than it's 1/2 xp, and then evaluated for the state measured. Okay. And this was h bar over half. And if you remember, h bar is a very, very small number, which is like, oh, we cannot measure exactly x and p, but we can get a pretty good approximation. Okay. This kind of uncertainty relations, they have many applications, for example, even in cryptography, for things like I encode a message into one basis, and if the other person does not know which basis to measure in, I know that they have like some total uncertainty about how well they can measure. It has many applications. We cannot get into all of them now, maybe in the next course. But what you can do is to prove this thing here. But first of all, what is exactly this measuring? What is the operational setting of this is the following. So I have some states, some input state. Suppose it's a pure state, you'll do the mixed state. And then here I make a measurement. And it's not I do one and then the other, as I do one or the other, right? I do A or B. So then this is going to be, what would be the uncertainty on X if I had measured X, times what would be the uncertainty on P if I measured P. So it looks a little bit less operational than the other two. All of these settings can be related to that, right? It can also be related to how well I can define like a more fine-grained observable that would give me approximately the right statistics and so on. Okay. So we can prove this. Can we prove it in 15 minutes? I don't know. Let's see. So goal is to prove, we do it for pure states here, that if I have two observables, the product of the uncertainties in that setting is larger than 1/2 times their commutator evaluated on the state that's measured. And this is a nice proof that takes many, many ingredients. The first ingredient is, look, this delta A is what? This is just delta A squared. This is just a number evaluated for some states, so rho or psi, which is just, I have the observable squared minus the square of the observable, right? This is a number. but what I want to do is to define an observable that behaves like this number. So what I do is to define an observable delta A, which is A minus, where this is the average value for this observable for state rho, which is just a trace of A. Now, no, this definition is state dependent. It's just going to be used. It's not something we're going to actually measure in the lab directly. It's just a mathematical tool that we use. So this is an operator. This is a number times an operator. Overall, it's an operator. And the claim is that if I take this, then I take the square of this, and I take the average of the square of this, then this gives me exactly the quantity I'm looking for. Oh. Okay, so good. This is the number I'm looking for, depends only on my observable A. I will do it by defining this intermediate observable and then doing this funny average that will give me the right result. Why? Because later on we'll work only with this operator. It will make all the calculations simpler. Okay, I mean, let's do this. It's very easy to prove. What is rho? So this is trace of rho delta A, right? And this is what I define it there in blue. So it's trace of A squared minus identity. This number A squared minus identity. This number A. Oh, sorry. So okay, we have 4 factors here. So let's just do them one by one. The first factor takes this A squared, and that. Is that correct? Sorry, I invented a square here. Yeah, good. So it takes this A, and that. So that's trace of A square rho minus trace of, this is a number times the identity, then takes that, trace of A rho minus same thing here. So let's just put a 2 here, and then plus this. So that's trace of this number squared times rho. Okay. I want to have it all here. So this is what? Trace of A2 squared. This is exactly this, right? This is A square evaluation rho. Here the trace is linear, so this number can come out, and then I'm just left with trace of rho, which is 1, because rho is a density matrix, so minus 2 times this number. plus, and same thing here. Wait a second, there should be a square here. I missed here an A. I missed an A there. Okay, sorry. 2 times this number trace of a row plus, now again, this number comes out. Trace of row is 1. Right? Now, this thing here is just the same as this, it's just this average. Right? So this is here took. Okay, cut that down. And then I have -2 of one thing plus 1 of that one thing gives us -1 of the same thing. So that's the squared row minus a. Okay. Okay, so that's done. This is exactly what I wanted. So all I did was we defined this funny observable. It's obviously emission. If A is emission, identity is emission, all is good. And then I just show it has the right properties. I can connect it to the thing I'm actually wanting to compute. And now from now on, I'll only work with this. Then we need a few more ingredients, which I prove in the, okay, because we don't have so much time. I say some of them are proven in these handwritten notes, and you can just look at them. And some of them you do in the tutorial. The first one is to looking at the commutator between these two variance observables, right? And if you just look at them, I mean, you have this part that's going to be non-trivial, and then you have this part with the identities, which are going to commute with everything. So the only thing that doesn't cancel out is the commutator of A and B. Okay? This is very, very easy to prove. We can do it now. It's also in the lecture notes. The other one is a general thing about states, which you prove in the tutorial, which is the following thing. AB squared is always smaller or equal than AA. Okay, this you'll prove in the tutorial, but it makes sense, right? It's like I have the inner product between two vectors. So for that, not only does it matter the norm of each vector, which is it's computed here, this is just the product of the norms, but then there should also be the angle between them, right? Cosine of the angle between them, which is always smaller than 1. So that's what's missing here. So you get an inequality. That's it. The other ingredient that I'm missing is, I scan in the wrong order. So what is 6 should be 5, which is that if A and B are emission, then the commutator is anti-emission. Okay, you have an example, for example, X and P is I H bar identity. This is an emission operator, and then you have the I there. This is true in general. The way to do it is to just take this and then take the dagger and see that you get exactly the same, but with the minus sign. So it is anti-emission, which means, like we saw in one of the very first lectures, it's an emission operator times the imaginary constant I. Good. And likewise, the anti-commutator, which is just AB plus BA, is permission. That makes sense, right? Even just looking at this, if A and B are emission, then the product is emission. And so, no, not that product, but the sum of the two versions of the product. Okay, good. And then the other one, which is also very, very trivial, is that the product of two matrices can always be written as the commutator plus the anti-commutator with some factors of 1/2. Right, it's like with the anti-commutator, you have AB plus, I don't know why it's F and G, but with the anti-commutator, you have AB plus BA. With the other one, you have AB minus BA. So these terms cancel each other, and you're left only with that. With a factor of 2, take the 1/2. Fine. Okay. Good. So then all's left to do is to prove the uncertainty relation. All right. And we'll do this. We might go a little bit over time, and then I'll let you go. In fact, nobody's keeping it in the room. So now I take the product of these two observables that I defined, right? And I just say, well, first of all, I use this last ingredient I use, and I say, well, this is just the anti-commutator, so the commutator plus the anti-commutator, delta A, delta B. Okay. Now this is 1/2 of, I use the ingredient number 2, this one here. Say, well, this is just the commutator of the original observables plus whatever was there. Okay, those two. Now I'm going to use this fact that if A and B are emission, then the commutator is anti-emission plus 1/2. And the anti-commutator is going to be Hermitian, it's going to be some K prime. Right? So this was so number 4. Yeah. Okay. That's all good. So now I'm going to take the average of this for some state psi. And this is what? Well, then this is going to be, let me write it like this. I psi, because everything is linear, so you get check over 2 plus psi over 2, right? Now, this is a number because psi is a pure quantum state and K prime is Hermitian, then this is a real number. Okay, so this is A, which is a real number. This is, again, a real number for the same reasons, right? But this I here. So this whole thing is like alpha plus I beta. It's a complex number. That's all I wanted to say. Okay, good. Why do we care about this? Because then if we take the absolute value, delta A, delta B of this, well, that's the absolute value of alpha plus I beta, which is what? This is alpha squared plus beta squared, right? And this is always larger than beta squared, okay? Because this alpha squared, now this is larger than 0. Okay, so this is where the inequality comes in my bound. Okay, what was this beta squared? So this was psi K over 2 psi squared, squared, which is same as psi. And now here comes the commutator, AB over 2 psi squared, right? Because of course there's an I sign here, but the I, or minus I even, but this goes away when you take the modulo square. Okay, very good. So let me just move things a little bit up. We're almost done. So what is this? Well, this is then 1/4 of Jack AB Jack, right? Because I just took the 2 out of the square, so it becomes 4. Good. So now what we have, if I plug in the first thing that we did, what was this? This, I said that delta A squared. So this is the actual uncertainty, not the uncertainty, not the variance observable. This was the same as delta A squared evaluated for state 5, right? This was this. Which means that if I just want delta A, I take the square root of that. Good. So then if I want delta A, delta B, the product of the 2 uncertainties, this is the square root of this delta A squared for phi, delta B squared for phi, right? And this is this thing that I was just computing here, right? Right, yes, so this whole thing is delta A, delta B. There's a mistake here somewhere. Okay, I will write down here the I'll write here the final thing, and then we'll check where the mistake was. Okay, so this is what we computed. AB chook, and then we simply take the square root out, and then we get 1/2 of AB chook, which is what we wanted to prove, right? Now I just got lost somewhere, which is when I use this thing here. Oh. Okay, I'll fix this for next time. But this is the main idea, that we use all these bounds like so. So an example is that, of course, we talked about X and P, but also as X, the uncertainty between the 2 spins, sorry, delta, is always going to be larger than 1/2 of SZ evaluated for the state psi, right? In the case of X and P is not state dependent, the bound, but for others, it's always going to be state dependent. This because this X, this Y, this what, up to factors of 2 everywhere. Okay, so the only thing that is not super clear here is how I did this step, but I'll fix this next time. Okay. And in the tutorial, we're going to see what happens if now instead of a pure state here, you have a density matrix, and it's not going to change that much. Okay. Now, the last word about this is that one can think of more operational uncertainty relations that depend on the entropy of the observable, not so much on the eigenvalues of the observable per se. And there's a lot of work on this. You can look, for example, at Roger Kolbeck's papers on this. Okay, I will stop here, let you go for lunch if you haven't started already, and see you on Thursday for the final lecture. Thank you. And if you have questions, I'm here now. Okay, just for the record, I forgot one step in the tutorial. Yeah, which is the beginning of this proof here, where I relate these things to the squares of the observables. Yeah. I'll write it here. You can go home. You can go have lunch, and I'll just write here the missing steps. If you want to see, you can, but so the missing steps here. Was now taking each of this and saying, well, delta A squared took for psi, this is what, this is psi, delta A, psi, just.
Sorry, may I ask a question?
Yes, of course, yes. Yeah.
Maybe I open this. Yeah. So I was just not sure about one slide about a map from involve of row A and with environment state.
So not this one?
No,
Not
this
one. It had a diagram?
Yeah, this one. So I was not sure why the uncertainty, the density matrix after the, I don't know, the involution or the map epsilon here, and then we get a density matrix rho prime. What I am confused is why this rho prime is it can be in a different Hilbert space.
Right. So in this, yes, okay, yeah, I get the question.
Yes.
So in this very first example, it's the same Hilbert space because it's just applying a unitary there, right? But more generally,
yes,
in this thing, so say you have, for example, m qubits here and n qubits there, right? So overall, here you have m plus n qubits. But then you can say, well, I only care about k qubits. So I trace out m plus n minus k in this other environment, right? And I should, the state of this k qubits is still a physical state, is still a density operator, right? So I should still be able to represent it by a map from the original thing to the final thing. So physically preserve the number of qubits, right? You have m plus n before the evolution, m plus n after the evolution. But then what this means, I can ignore as many as I want.
Oh, so this k qubits here that we have, that we can observe or we want to observe must be smaller than m?
It must be smaller than, well, it must be smaller than the whole thing.
The whole thing. Okay.
Yeah, then the whole thing, yes. Yes, because so an example where it grows is, for example, let's do it classically.
Yes.
Huh. Yeah, let's do it classically. That for example, something like a repetition code. I start with A, I end up with A. Right? So I go from 1 bit to 3 bits. But this is still a physical evolution, right? In this case, it's like I entered. So in this case, it's like I had A here and I had 0, 0. And then this went all to A. And I can say, well, maybe I care about all of these qubits. So classically, you cannot do what you can do is, so if alpha 0 plus beta 1, for example, in your system S, 1 qubit, and then you bring in 2 qubits in system 0 from the environment. And you can apply this map that takes to alpha 0, 0, 0 plus beta 1, 1, 1, right? And I trace out nothing. Or I trace out the first qubit. I say I don't care about the first qubit and I only care about the other 2. Then I get here the alpha squared 0, 0, 0, 0 plus beta squared 1, 1.
Okay, so
so tracing out is really, so imagine I have a reversible operation in a larger system, and now it's really about what do I care about, what do I want to follow, how many qubits do I want to follow. I care about what is the local effect of this map on my system of interest.
Okay, I see. And let me think. Okay, I see. Maybe I will think about it more. Yes.
Think about it a bit, and then you can ask me again on Thursday.
Yeah, thank you. I got it.
Thanks.
Yes. Yeah.
Thanks.
Bye. Yeah.
I'll just continue writing this thing to make sure we got it right.
Okay.
Okay. So I'll just finish this. Yeah, so then the idea is saying, I have this, and now I say, well, delta A is Hermitian, so I can put here the dagger. So now I call this the state A. This is just A. So then I have that delta A squared, delta B squared, evaluated for psi. This is A. I do the same on B, so I get BB. And then I use this result number 3. To say, well, this is larger than AB squared. This is this result I did a while ago that we prove in the tutorial. And then here we have, finally, this is what? This is psi, delta A, delta B, psi squared. So now you can indeed say that this is larger than psi, delta A, delta B, psi squared, and then the square root. And this, from what we said before, is larger than 1/4 of psi, the commutator AB psi, and that's 1/2 of this. Okay. Now we've finished. Okay, that's it. Good. So that's the finish of the uncertainty relation. Read Roger's papers if you want to know more. Bye.